So this Euler's method, so already we learned Range-Kutta method, and Euler's method is also similar. It works on the similar concept, and this is the extension of Taylor series method. So in case of a Taylor series method, this concept utilizes a tangent concept, and the Taylor series will be truncated up to first derivative. So that we will understand how we can obtain the equation for Taylor series. First of all, you look at this diagram. Okay, so I will make this as a. So look at this diagram. So this is the function or a curve. So this curve is represented by its slope. The slope of this curve is represented by dy by dx is equal to function of x, y. So this is the given equation. In case of a numericals, always we will get the equation in terms of dy by dx. So that is represented by function. So the dy by dx is function of two parameters, x and y. Now here, so you know x1, so x0 value. So you draw a vertical line from x0 point. So it will be intersect somewhere to this curve. So from that point, you draw a horizontal line. So you will get y0 value. So simply it is written, so here itself it is written y0, and actually this is y0 because this is the y function and this represents x coordinate and y coordinate. And the point on the curve is represented by A, so its coordinates are x0 and y0. Similarly, so there is a one more value, say x1. So you are intersecting this x1, drawing a vertical line from x1. It intersects the curve at point B. So its corresponding coordinate on y-axis is y1, and the point B or B dash can be represented by x1, y1. So here h represents the interval between these two. So h, similar to previous case, it is x1 minus x0. Difference of these two is h. Now this Euler's method is works on the concept of tangent. So we know the initial coordinate because in all problems, so we'll get a boundary conditions y at x0 is equal to something. So we are calling this as a y0. So value of y at x0 is equal to y0. So here we will get some value of x0 and y0. So these are all called boundary conditions. Now here, so you can see, so this is the point A. So we know from the boundary conditions, so x0 and y0 value. So once you know the x0 and y0 value, so A x0 y0. So this is the point A. So because it uses the tangent concept at point A, so we are drawing a tangent line. Here you can see a tangent line. So this tangent line, by using this tangent line, so we can derive the equation for computing new value. So that is y value. So y value means y1 value. So that can be computed by using this tangent concept. So in the tangent concept, first of all, you can consider this is the point B, and here actual B dash point. So this point is lying on the curve here, but we are considering this because we are utilizing a tangent concept. So this is our tangent line. So on this point, I am referring this as a B point, and this is B dash point. Here also it is represented. This is B dash point. Now you draw a horizontal line. So consider a triangle ABC. So this is point A. So this point is B, and this is point C. So here you can represent this by a triangle. So this is ABC triangle. So consider this ABC triangle ABC. Now tan theta, we are assuming that this is so very negligible uh, angle. So or simply you can take theta as a small angle. So here you can write tan theta is equal to opposite by tan theta is equal to opposite by adjacent. So what is the value of opposite value? Opposite value you can write this BC. So this distance BC upon adjacent is AC. AC is represented by H. See BC. So how do you write BC? So this is the value Y1. Y1, and here what is the value? So at this point it is Y0. So this distance is BC. So you can write BC is equal to Y1 minus Y0. Same thing it is written Y1 minus Y0 upon H. Now here what is the tan theta? So tan theta also represented by using slope. Slope is equal to tan theta. So that you can write dy by dx. Slope is equal to tan theta is equal to dy by dx. So this dy by dx is equal to function of xy at a point A. See the function of, so the slope is a function of point A. So there we have taken value coordinate point function of xy. So xy can be represented by a coordinate x0 and y0. Say because a coordinate is represented by x0 and y0, and this tan theta or the tan theta is replaced by slope. So that is dy by dx. So this dy by dx. Okay, I will write here dy by dx. So this dy by dx is replaced by this function f of x0 y0, and this is equal to, so this is equal to tan theta. So that is tan theta is equal to y1 minus y0 by h, and dy by dx is equal to this. So here, so we have equated, so this tan theta, and again tan theta is equal to this from here. So we got one relation. So you rearrange this equation in terms of y0, but because our intention is to find so this value based on y0. So therefore you rearrange this equation so in this form, and finally we need this in terms of y1 because we would like to find this new value y1. So this is in terms of y0 plus h into f of x0 into y0. So this is the equation which is derived based on the tangent concept, and this equation is called Euler's equation. This equation is called Euler's equation. You need to remember this equation, Euler's equation. And the drawback of this method is for small h. So this is the h, smaller h, error is bounded to be a quite significant. So this method is very slow. So because so we have to use n number of iterations and it is slow. If a small value of h you will take, so error bounded to quite significant. So this is about Euler's method.